So let's talk about the second example where we are going to try to find out the mass and the center of mass of the lamina bounded by the graphs of the equations for the given density. The given density is again a constant continuous density of K, and the lamina is bounded by the curves y equal to 25 minus x squared square root. So think about this, y equal to square root of 25 minus x squared. If I square both sides, I get y squared equal to 25 minus x squared. Then I add x squared to both sides, I get x squared plus y squared equal to 25. Remember, this is a circle of radius 5 units. And the other thing is 0 less equal to y less equal to x. If y is equal to x, then that's the straight line making an angle of 45 degree of pi over 4 with the positive direction of x-axis. So the lamina is bounded by the line y equal to x and the circular boundary of y equal to square root of 25 minus x squared. And this is your region of integration. So those things kind of suggest that I should look into the polar substitution. Why? Well, think about your polar substitution are x equal to r cosine theta and y equal to r sine theta. So x squared plus y squared becomes r squared cosine squared theta plus r squared sine squared theta. And that is equal to 25, means r squared is equal to 25. So r is equal to 5 because radius cannot be negative. I will just take a positive value. That's a much easier limit to deal with. R is equal to 5. What else? So think about the line y equal to x and do the same substitution. So you will get y, so r sine theta equal to x, which is r cosine theta. Divide both sides by r cosine theta. You get tangent theta equal to 1. So theta is equal to arc tangent of 1, and that's pi over 4. So since I'm integrating over this closed region, my value of r is bounded between 0 and 5. So I will say that this is the limit for r, whereas the angular measure starts at 0 and goes all the way to the line y equal to x, which I know is pi over 4. So theta is between 0 and pi over 4. These are your limits for the integration. So let's talk about the formula for the mass. The mass is integration over the region of the continuous density function with respect to the area, which I'm going to do in polar substitution. So let's do the integration with respect to r first. The limits are 0 to 5. Your density is k, and remember polar substitution requires you to multiply this r. You're doing integration with respect to r first. Limits of theta are 0 to pi over 4, and see how simple this antiderivative is. I take this constant k outside, and the antiderivative of r is r squared over 2. And then I'm going to put the limits for r, which are 0 to 5. I still have to do the antiderivative with respect to theta. So I get 25 over 2, which I take out. And then I do antiderivative of theta, d theta, between 0 and pi over 4, which is going to be simply the constant pi over 4, as antiderivative of d theta is theta. You will put it in limits 0 to pi over 4. So theta equal to 0 will not give you anything. Theta equal to pi over 4 is going to give you 25 pi over 8, and somehow I forgot the k. I should have had the k here. So this is 25 pi k over 8, and that's the mass of this lamina. So you know the next step, we're going to talk about the center of mass. So we're going to find out mx. So let's first write down the formula. It's integration over r, y times rho xy dA, and as we have recalled, we're going to do this antiderivative with respect to r and theta. So I'm going to go ahead and say that limits of theta are 0 to pi over 4, limits of r are 0 to 5, y is r sine theta, rho is k. For the Substitution in terms of r and theta, I need an r times dr times d theta. So k should be coming out, integration 0 to pi over 4. Let's see what else we have. We have sine theta, which has nothing to do with this entire derivative with respect to r. So I take it out. And you have r square, which you are going to take the entire derivative with respect to r, which is going to be r cubed over 3. So what I say, k 0 to pi over 4 sine theta r cubed over 3, limits are 0 to 5, and then you do the entire derivative with respect to theta. Okay, so I get, when I put r equal to 5, I get 125 over 3, which I'm going to take out. So I get 125k over 3. Antiderivative 0 to pi over 4. Recall that if you put r equal to 0, it doesn't change anything, so I'm not going to use that at all. And I have sine theta d theta. Well, antiderivative of sine theta is minus cosine theta. So you get minus 125k over 3 times cosine theta, limits are 0 to pi over 4. So I get minus 125k over 3. Cosine of pi over 4 is square root of 2 over 2. And cosine of 0 is 1. So you get, if you now push this minus in, I will get 125k over 6. Why 6? Because the common denominator in this subtraction is 2. I bring that 2 out. And inside, I will get 2 minus square root of 2. Because I have pushed in the minus. So this 1 you can think is as 2 over 2. So I get square root of 2 minus 2. But because I pushed the minus in, it has become 2 minus square root of 2. So that's precisely what mx is going to look like. I have one more step to do. And that's finding my. Well, my, by the formula, is antiderivative of the region of the Lambda-States area, and you do x times rho x comma y dA, which in our antiderivative terms is going to be 0 to pi over 4, 0 to 5. X is r cosine theta times k is the density times r from the Jacobian from the transformation, times dr d theta. Take the constant k out. You get 0 to pi over 4. And then you have 0 to 5 r squared dr. Recall cosine theta has nothing to do with this antiderivative, so I take it out. And d theta. So what I get, like the last one, you get k times cosine theta r cubed over 3 between the limits of 0 and 5 d theta. So again, it's 125 over 3. I will take it outside. And antiderivative of cosine theta is just sine theta, which evaluated it in the limit of 0 to pi over 4. So I get 125k over 3 times sine of pi over 4 is square root of 2 over 2, and that's it. Sine of 0 is 0. I don't even worry about that. So this is 125k square root of 2 over 6. So center of mass is my next objective. And I just want you to remember, for the center of mass finding, you're going to use the formula my over the mass, comma mx over the mass. Remember, your my we just found out as 125k square root of 2 over 6 all over the mass, and we found out the mass equal to, I believe that was 25 pi k over 8. Comma, mx was 125k over 6 times 2 minus square root of 2 over the same mass, 25 pi k over 8. So we're going to simplify this quantity and we will have the answer to the question for finding the center of mass. So I can go ahead and write it as 125k square root of 2 over 6 times 8 over 25 pi k, that's the x coordinate, comma 125k times 2 minus square root of 2 over 6 times 8 over 25 pi k. That's the y coordinate. So after cancellation, I get, see the k and k cancels, 25 cancels, 125 gives you 5. So you get 5 times 4 times square root of 2 over 3 pi, comma. Similarly, you get 5 times 4 times 2 minus square root of 2 over 3 pi. So I get 20 square root of 2 over 3 pi, comma, 20 times 2 minus square root of 2 over 3 pi as the coordinates for the center of mass. In our next video, we would like to talk about moment of inertia.